All right. So the proof of the Riemann mapping theorem breaks into two different parts. One part is using results from complex analysis, and the other part is using just some standard facts from real analysis. So this is a great way to review a lot of the stuff you've seen in real analysis and see why we care about it. So to save myself a little bit of time, I'm just writing the stuff down here. This is all in your notes. You can try to write it down quickly now, or you can just look at it later. I want to try to leave this on the board as much as possible. And tell me where you see me writing something a little bit strange in terms of my handwriting. So we'll say something is normal if every sequence of functions in a set of functions f has a subsequence of functions that converge uniformly on compactor. A sequence of functions will be uniformly bounded on compactor if for any compact k there exists some constant b of k such that for all z and k, for all f in the family, you have f of z is less than or equal to b of k. Yes?
Sorry, I've never heard the term compactor.
Basically on compact sets. It's a way to just sound a little bit fancier. Has anybody seen anything strange with my handwriting yet? That's how I was taught to do Fs. The K's and the B sub K's. This is a little bit different than the book. I like to have subscripts on my variables and my constants so I can keep track of where things live, especially when you have things varying. So we have a sequence of functions, and we're going to have lots of different compact sets in play at once. I want my bound so I can quickly glance down and say, okay, this bound depends on the specific compact set K. The next is equicontinuous on K. So for all epsilon greater than 0, there exists a delta. Again, delta depends on K, such that if z and w are in K, and z and w are close if they're within delta, then f of z minus f of w is less than epsilon. Exhaustion. This is not when you've been doing an all-nighter. It is when you have an open set omega. You can write it as a limit of compact sets. This is not going to be too hard to do. What we can do is essentially we'll take our compact sets to be all the points that are at least 1 over L from the boundary of omega. And then as L gets larger and larger and larger and larger, you can see the compact sets will be expanding upwards. Now there's only one problem with taking sets that are within 1 over L of the boundary. What's the problem? You have to be a little bit more careful. Because this seems like we should be able to get everything. If your set is unbounded, then you might not get everything if you're just taking everything within 1 over L of a boundary. So what you can always do is you take all the points within 1 over L of the boundary, intersect a circle of radius L. And then the radius of the circle is going off to infinity, the distance to the boundary is getting smaller and smaller and smaller, you'll get every point. And so this will give you an exhaustion. The idea is we always want to be working on good sets. We like to work on open sets, so we have a small neighborhood about our point entirely contained. Compact sets are nice. We have certain results that hold for compact sets. And then the big result for today is Montel's theorem. If F is a holomorphic family of uniformly bounded on compact sets, then the following two hold. 1, F is equicontinuous on compact sets, and 2, F is normal. The second one is called the Azella-Ascoli theorem. You probably have not seen it in real analysis, but you could have seen it in real analysis. This one does not have any complex analysis in it. The first one does. So the question is, if we restrict ourselves to real functions, can we find a counterexample to 1? So holomorphic, so instead of holomorphic, what should we choose? What should be the real analog of holomorphic? Infinitely differentiable. So if we take an infinitely differentiable family that's uniformly bounded on compact sets, then is F equicontinuous. So equicontinuous would mean if you have two things that are really close, then they have to be extremely close. So there's a lot of good examples you could use. Any thoughts on what would be? So one of the good examples, and I'll let you think about this, is sine of nx. If you look at what's going on in minus 1, 1, sine of nx, as n gets very, very large, the period is becoming extremely small. It's oscillating wildly. So if you want things to be close, you're going to have trouble with sine. Right? So try to play the games with sine and see that things can go violently wrong. And so if things are going wrong in the real case, this means we somehow have to use something that's fundamentally complex if we're going to prove one. What big results do we have? Well, when we have holomorphic functions, this means it's differentiable once. It means it's infinitely differentiable. It's given by its Taylor series, and we even know where the Taylor series is coming from. The Taylor series is coming from contour integrals of the function on the boundary of a small circle. This is the Cauchy residue theorem. Not the Cauchy residue theorem, the Cauchy integral formula. When in doubt, say Cauchy something. The Cauchy integral formula. So this gives us an idea of what we might want to try. One thing that's interesting, and this was actually one of the key results I need to use in my thesis, is if you have a function whose first derivative is bounded, then you're often in great shape. Then you can use the mean value theorem. And if the first derivative is bounded, then f of x minus f of y by the mean value theorem will be less than or equal to f prime at some intermediate point times x minus y. So if your first derivative is uniformly bounded, you will be equicontinuous. So if you start looking at functions like sine of nx, you can see the first derivative is not going to be uniformly bounded. Another thing that people often look at is the function x to the n, where you'll have these n's coming down. This is where the violence is going to happen. This is where things are going to break down. Okay, so again, you want to get some sense as to why these things are true, why they are not true, what can break down. All right, so we are at least swiveling now, which is good. All right, so what we want to do is we want to prove Montel 1. Okay, so proof of Montel's theorem, part 1. So what this means is we have a holomorphic family uniformly bounded on compact sets. Then we need to show it's equicontinuous on compact sets. Okay, what does it mean to be equicontinuous on compact sets? It means given some compact set, if we take 2 points that are very close, then the difference in the values of the function has to be very small. Okay, so what we're going to do is, if we have a compact set, what's nice is a compact set is closed, our space omega is open. So there's going to be a separation between our compact set and the space omega. We have not used too many results from real analysis up till now. It's about time we start using some results from real analysis. When you think of a compact set, what do you think about a compact set? What's a big property compact sets have? Closed and bounded. What else? Functions attain maxima and minima. What else? Every sequence has a subsequence that converges. What else? This is a nice way to review. You haven't hit it yet. Yes, there we go. Every cover has a finite subcover. Okay? Why do we care so much about that? What that means is we can convert an infinite problem into finitely many problems, do our analysis at these finitely many points, and then piece it together. That's why compact sets are going to be so nice for us. Okay? So what we can do is take compact, let the distance from k to the boundary of omega be greater than 5r. So you give me any point in k, its distance to the boundary of omega is going to be at least 5r. Omega, remember, is an open set. Okay? So now, given any point in k, draw a ball of radius, and I want to make sure I keep things correct. I think I want to take 3r. Ball 3r. What can you tell me about any ball of radius 3r about a point z in k? It's an omega. Remember, our functions are known to be holomorphic in omega. I want to make sure we stay in omega. So if you want, here's the boundary of omega. Think of this as our k. And we take some point here. We take a circle of radius 3r about our point, and we're still going to be inside omega. We might be outside of k, but we will still be inside omega. Okay? So now I think what we're going to do is we're going to take a circle now of radius 2r about a point. And so what we're going to do now is I'm going to zoom in a little bit. So here's some point w. Here's a big circle of radius 3r. Here's a smaller circle of radius 2r. And here's an even smaller circle of radius r, not drawn to scale or concentricity. If we choose z and w to both be inside the circle of radius r, they'll be very close to each other. They will not be too close to this boundary circle, and they'll still be inside omega. So we will want z within r of w. And we're going to think of r as delta. So they're going to be very close to each other. We want to figure out how far apart are f of z and f of w. Any idea how we can get values for f of z and f of w? So in complex analysis now, you've got to have something that's not available in real, because this theorem is not true for real. What do we have available for us now? If I want to figure out the value of f of z or f of w, how can I do that? I'm sorry? We could do that, and how would we get the terms in the Taylor series?
I guess that is available to us in real.
If the function's real analytic. But we have a really nice interpretation of f of z. We have a nice way to get the value f of z. What gives us the value? Cauchy's integral formula. By Cauchy's integral formula, f of z minus f of w, and I'll just put in absolute values, is less than or equal to the absolute value of 1 over 2 pi I, the integral over a circle of radius 2r. We'll have it centered at w. And then it'll be f of zeta over zeta minus z minus f of zeta over zeta minus w d zeta. So this is the Cauchy integral formula. This is going to give me f of z. This is going to give me f of w. And we can write this down because we're being very careful and we're staying inside omega, so Cauchy's formula holds. All right. This is, you've got to have in your bag of tricks Cauchy's integral formula. This is something that is not typically true in the real case, is we can give the value of our function at an interior point from doing an integral along the boundary. And now if we have some control over what's going on for our function on the boundary, we get control on the inside. Well, what are we assuming in Montel? We're doing Montel 1. And so Montel 1, we assume we have a holomorphic family uniformly bounded on compact sets. Well, this stuff over here, there we go. Now, what is the bound for f over here? What should we call that bound? You might worry that maybe it's not the bound from the compact set K, because we're taking points that could be within 2r away, right? So I would say that this is not K, this is maybe K prime. It's k expanded a little bit because we are allowed to go a little bit beyond.
So just to clarify,
Yes.
K is contained
In omega.
inside
Yes. And so is, if we take everything in k and we push forward by a little bit, we'll still be contained in omega because I'm choosing the distance between k and the boundary of omega to be greater than 5r. This is another place where we're using some of the other results that was mentioned about compact sets. I can't remember, it was from this half of the room, that said if we have a compact set, any function attains its max and minima. So if we look at the function distance from any point in k to omega, as we vary over points in k, that's going to attain its minimum value. Let's choose 5r so that that is less than the minimum value. And the minimum value will be greater than 0. So again, when I try to bound my functions f, I might be slightly outside of k. So I might be on some set k prime, but it's going to be fine. So now I continue the analysis, and I get this is going to be less than or equal to, I have a 1 over 2 pi. When I bound the absolute value of f, I'll call it maybe bk tilde over 2 pi. And now, what's the perimeter of this circle? This is where I think the book makes a mistake. What's the perimeter of the circle? 4 pi r. The book, I think, drops a 2. It's 2 pi times 2r, because we have a circle of radius 2r about w, not a circle of radius r about w. Doesn't matter. Now we want to look at zeta minus z and 1 over zeta minus w. What can you tell me about zeta minus z? How big can that be? So what's the small, we have trouble when zeta minus z is small. What's the smallest zeta minus z can be? R. And what about zeta minus w? 2r. Right? So if we look at this, zeta minus z can't be too small. Right, now, if we cross multiply, we get zeta minus w minus zeta minus z. So that gives us a z minus w upstairs when we cross multiply. And we have a zeta minus z, zeta minus w. And now this over here is going to be at least, I'm going to be at most r, sorry, it's going to be at least r, so the reciprocal is going to be at most 1 over r. Over here, this is going to be exactly 1 over, this is going to be 2r, so it's going to be 1 over 2r. So this is then going to give us less than or equal to bk tilde, the 2 pi's cancel, so I guess I don't have to write this so high, bk tilde, then we have a 2r. Down here, we're going to get a 2r from this, which will cancel with this, and we'll get, I guess, a 1 over r from this. So we get a over r times z minus w. And that's because 1 over zeta minus z is less equal to 1 over r, and 1 over zeta minus w equals 1 over 2r. So our goal is to show equicontinuity. We want to show that f of z minus f of w is less than epsilon as long as z and w are really close. So we already knew we were going to have z and w within delta. Oh, okay, that's not really saying much, that's just definition. What is delta? We knew delta was going to be less than r. Now we can see exactly how much less than r it wants to be. So for this to be less than epsilon, need delta to be less than, I think, epsilon r over bk tilde plus 1. And if we take that, we will be fine. Yes?
So how did we pop outside the integral? Were we assuming that f attains some...
Well, right, because by Montel's theorem, our assumption is f is uniformly bounded on compact sets.
Okay.
And then note that the bound is not necessarily on k. It's expanded a little bit.
Got it. So bk is the bound.
Right. bk tilde bound from expanding k by r. We have to expand it out just a little bit, and then we're OK. Why did I put the plus 1 down here? Most people do not do this. You should put the plus 1. Why should you put the plus 1?
If it's bounded by 0.
If it's bounded by 0, do you really want to worry about having written down dividing by 0? So just to be safe, throw in a plus 1 down there. You've got room to play with. You've got some safety margin. Use the safety margin. OK? Any questions on Montel 1? So this is a nice result. It uses a lot of information from, just see if this is working. No, it's not even swiveling anymore. This uses a lot of stuff from complex analysis. This is not a proof that could work in the real case because we are using, crucially, the Cauchy integral formula. And again, you just want to keep getting in mind, I have the Cauchy integral formula, I have holomorphic is analytic, I've got Boucher's theorem, I've got open mapping theorem, I've got max modulus principle. These are the big cornerstones in complex analysis that you want to use whenever possible in your arguments. You want to keep track very carefully of where the bounds live. And it's very easy to make a mistake. We're not bounding f on k because since we're doing these integrals, we might be a little bit outside of k. But fortunately, it's not a big deal. OK, any questions on this? OK, I want to try to leave all these statements on the board. And so what I would like to do is I would like to erase the first part of this proof. And even more, I'd like the camera to swivel back with me. But I have put in a request for better swivel technology for next year. And so we'll see if it... No, not at all. This is... Oh, now it's working fine. All right. So I'll leave the other part up for just a minute in case people are still copying it down. All right. Proof of Montel 2. All right. So for Montel 2, what we want to do now is we want to somehow show that if we have a holomorphic family of uniformly bounded on compact sets, that f is normal. All right, so this one is a little bit more involved. Now, if we want to, are we allowed to use that f is equicontinuous on compact sets in the proof of Montel 2? Sure, we've just proven that. So then the question becomes, if you want to define the Zella-Ascoli theorem, do you want to assume you have an equicontinuous family on compact sets? Should that be one of the conditions? I would say yes. This is a key property. For our family, this follows from complex analysis. But we could consider just the case of a uniformly bounded on compact sets, equicontinuous on compact sets, and then prove that it's normal. So what does it mean to prove it's normal? It means given a sequence of functions in f, there's a subsequence that converges uniformly on compactor. So this is where we're going to use our method of exhaustion. What we're going to do is we're going to take our family of functions, and we're going to look at one compact set first. And we're going to show that it has a subsequence that converges uniformly on that compact set. And then we're going to basically just keep applying Cantor's diagonalization argument. Then we're going to take a slightly larger compact set, and we'll look at a subfamily of our original family. And there'll be a subfamily of that which will converge. And we'll then take an even larger one. And we keep going like this. So lots of stuff going on here. We want to show that it has a subsequence converging uniformly on compactor. One of the big things about compact sets is they have a finite subcover. So what we want to do is we want to take a really good small set of points, understand what's going on at those points, and expand. So can you find in a nice open set in the complex plane, can you find a dense subset? So how could you give me a really nice rule of a dense subset?
Do you want a...
Countable.
Okay, so just take all the complex numbers with rational.
Good. Of k from K intersect, we'll call it the points Q plus, IQ. So this gives us a countable sequence of points. And what we can try to do is we can understand what's going on at these points. And then do we need to understand what's going on at all of them? No. A finite number of them would be fine. OK, so what we're going to do is I want to try to follow the book's notation. I think they call it W1, W2, W3. OK. So it gives W1, W2, W3, dot, dot, dot. All right. So now, F is holomorphic, uniformly bounded. F is equicontinuous on compact sets. So the first thing is their claim there exists a subsequence, and they want to use Fn1, and goes from 1 to infinity, that converges at W1. So why can we make the claim that a sequence of functions has a subsequence that converges at the point W1? Do you think every function in my family has to be in my subsequence that converges? No. I mean, I could do something stupid and have my family alternating between +1, -1. And that's my family. So clearly, we don't expect that this is going to be true for every term in a generic sequence. There's nothing here that's giving us some kind of uniformity control, that these functions have some kind of property, that their absolute values are decreasing or something like that. This is just a general family. So we don't expect any results like this to hold for every element of the family. All right. That's bad, but it also suggests what might work. There was yet another property of compact sets that was mentioned earlier, that I poo-pooed earlier. I might have been overly condescending. It's going to be useful now. What do you want to use now? So we've done, any open cover has a finite subcover. We're going to be using, we've used already a continuous function attains its maximum and minima. There's another good property of compact sets. Sequences have convergent subsequences. So let's just look at all the values evaluated, all of our functions evaluated at W1. All we need to know is that that sequence is bounded, and then it will have a convergent subsequence. Oh, goody! Our family is uniformly bounded. Goody's a technical term. Right? Our family is bounded on compact sets. Why? Family is uniformly bounded on compactor. Thus, if you look at Fn of W1, has a subsequence that converges. So we're really trying to use all the properties we have of compact sets. So again, I know it's been a while since a lot of you have seen this stuff in real analysis. I want you to get a sense of where this is used. And to me, this is one of the best reasons to do the Riemann mapping theorem. It's extremely useful. It's going to allow us to say any two simply connected sets, simply connected open sets that are not all of C, are isomorphic under a holomorphic invertible map, which is phenomenal, which means if we understand the unit disk, we understand the upper half plane. We understand the automorphism group of the unit disk, we understand the automorphism group of the upper half plane. It's phenomenal. But it also allows us to review a lot of your results from real analysis and see how they're used. So we have a family that converges at W1. What should we do next? W2. And then W3. So continue find subsequence converging at W1 and W2. Let's call it Fn2. Then W1, W2, W3, we'll call that Fn3. And we can keep going on and on and on like this. Do we have to do this for all points? We could do it for all points, I think, if we wanted to, because it is countable. Or we could say we only need to do it for finitely many of them, because any open cover has a finite subcover, and for each one of these, draw a small little thing. We're at a compact set. There's a distance from the boundary. So you have a little bit of freedom in terms of how you want to try to do the argument. I think over here, the book is actually doing it for all of the W's. Yes. And so let Gn be the function Fnn. So this is a diagonalization argument. So we take the first term from the original sequence, and we take the second term from the new subsequence, and the third term from the next one. And what was nice about this is this implies Gn of Wk converges for all Wk as n goes to infinity. So this is the standard Cantor diagonalization argument. But now it's being used for more than just proving the cardinality of the irrationals is larger than the cardinality of the rationals. So how many of you have seen diagonalization arguments used like this before? Okay, so this is a very nice application. So we've got our sequence that's converging. What are we trying to show? We're trying to show it's normal. So we're trying to show we have a sequence that converges uniformly on compactor. Have we shown that it converges uniformly on compactor? So far, where are the only places we know the sequence Gn converges? Well, the rational points, or whatever our dense subset is.
Right, yeah, not necessarily.
Not necessarily everywhere. So what we want to do is we want to show that if it's converging at this dense sequence, come on, it's got to converge everywhere. And this is where we're going to now do a finite subcover, and where we're going to do a 3 epsilon proof. So a 3 epsilon proof is what you do when you become an advanced mathematician and you don't care about having things end up as epsilon at the end of the day. There's really no difference. It's just a question of how do you want to deal with the algebra. So draw balls and see what notation the book is using. Okay, radius delta. Draw balls of radius delta about each Wk. It's good not to call these points Wn because I'm using n as my index for G. I want to try to keep the indices separate. Okay? As K is compact, finite collection, say, we relabel W1. Oh, K is a really bad notation because K could be confused with, so, well, yeah, I'll keep these over here. Finite collection. I don't know if I want to use a capital F for finite. I don't want to use n for number because we've already got an n in play.
What an L used, right?
What about a capital?
A capital. I know, but then there's a lowercase n. I should really use maybe an L for the length. I don't know. Say WL have their balls covering K. Now, what do we have to be a little bit careful about? So this statement's a little bit too cavalier. It can be fixed, but as it stands right now, something dangerous could have happened. So any compact set has the property that a cover by open sets contains a finite subcover. So for each point we draw a ball of radius delta, and then we only need finitely many of them. What's the danger?
Well, it's a cover.
Mm-hmm.
So that's fine.
That's fine. What's the danger? Yes.
The number is going to depend on that radius.
That's fine. It's finite. There is some issue though with the radius. What could happen? I've said we've drawn balls of radius delta about each WK. What could happen if I'm not careful about my radii?
One ball.
I'm sorry?
You could have one ball.
Works for me. Less work.
If they're too large, then our function doesn't behave.
If they're too large, what might we leave?
Omega.
We might leave omega. Make sure delta is small. Stay in omega.
But aren't we going to leave omega whatever delta we choose if we cover the
No, because remember, omega is open, k is compact. No. We're being really careful in terms of where we work. This is why I'm constantly checking down with my notes to make sure. I want to make sure we stay in compact sets when we're supposed to, and we stay within omega, because it's only within omega that we know things are fine. So again, this is why you have to be very careful about what your constants are. If your constants depend on the compact set, when we take this open cover, we could have inflated things just a little bit. And it may not be the same compact set K, but it will be a closely related compact set. So it's not going to be a huge deal. So now what we can do is say, I want to use the same notation. We're going to use, I think, the points. Oh, I didn't even bother doing it. All right. So here's our point Z, and here's our point W. And we want them to be very close to each other. We're trying to show that that G converges at some point Z. Okay? And so what we can do is we can definitely find some WK very close to Z. And we want to pass convergence questions about what's going on at Z to convergence questions of what's going on at WK. And so we would get G of Z minus G let's see. I think maybe I'll do like a Cauchy condition. So we want 2 points that are very close to each other. And if we can show that that distance goes to 0, then that proves the sequence G is Cauchy. So there should be some intermediate point, so that this would be like Gn of Z minus Gn of WK plus Gn. I'm missing a point. Okay, maybe there's like WK minus Gn of WL plus Gn of WL minus Gn of W. So I want to do this. So here's Z, here's W, WL. Okay, so can I do the argument this way? If I show that Gn of Z minus Gn of W tends to 0, this proves that the function G is Cauchy. Is this correct? Is this fine for 3 epsilon proof? Let's see. Let's see. Which we're trying to show that the function G converges at any point Z. And so I don't really know what my limit function G is. And so I believe if I just take any 2 points that are sufficiently close, and I show as n goes to 0, oh, wait a minute, this, no, but, oh, wait a minute. Oh no, I've got to take I want to take a sequence of points, I think, converging to z, right? So now I'm screwing this up, so let me think. Let me think this again. So maybe we have a sequence of points zm converging to z.
And those zms are in W?
And these will all eventually be in W. So there'll be some WK here. And eventually all the points ZM will be in W. And we want to show that G of ZM converges to G of Z as ZM converges to Z. So we would want to look at G of ZM minus Gn of Z. And we want to show that this goes to 0. And then that would prove that the functions Gn are converging at the point Z. Okay, this would then be Gn of Zm minus Gn of Wk. I just feel like I'm dropping a point.
Did you say that the sequence Zm eventually contains only rational elements or elements of WK?
No, Zm is just some sequence that is approaching Z. So Zm is getting closer and closer to Z. So Gn of Zm minus Gn of Wk I'm pulling it off by one thing. Let me quickly. So here, does somebody have their book on them? Or so I am dropping 1 point right now in terms of where I do things. So I think this will be faster than pulling it up from my notes. All right, so I apologize on this. This is a 3 epsilon proof, and I'm dropping one of the middle pieces. Okay, so all right, so we've got our function as before.
Equicontinuous piece?
Yes, so we've got our diagonal pieces. By the definition of equicontinuity, the set K is contained in the union of disks. We've got that. We're picking n so large that Gm of Wj, okay, minus Gm of, so Gn of Wj is less than epsilon. And then what we're going to do is we're going to look at Gn, oh, okay, this is what I was doing wrong, minus Gm of Z. That is less than or equal to Gn of Z minus Gn, okay, of Wk plus Gn of Wk minus Gm of Wk plus Gm of Wk minus Gm of Z. All right, that's the mistake I was doing in terms of the Cauchy. Is the middle piece we need to do. Okay, sorry about that. Okay, the middle piece we need to do is we have Gn and Gm. The Cauchy criteria is we're not changing different points here, we're changing the index. That's where I was making the mistake. We need to take one fixed point, and then at that fixed point, if we take the two indices sufficiently large, their difference is arbitrarily small. That gives us the Cauchy criterion for convergence. And then what we're going to do is we're going to be adding intermediate points. So we're going to be adding 0 twice. And the way we add 0 is we do Gn at Wk and Gm at Wk. And so we've added 0. And by adding 0 like this, this is now having us going on with Gn and Gn at the point Wk. This is having us go on at Gm and Gm at the point Wk. And then over here, we know we have convergence at Wk. So really, what we're doing is we don't have a sequence of points Zm. We have some fixed Z that's in a ball about Wk. And we're going to be choosing two different indices, n and m. And n and m are going to get very, very large. So the first thing we do is we choose n so large that Gm of Wj minus Gn of Wj is less than epsilon, as long as m and n are greater than or equal to n. Now we can do this for all the balls at the same time because there's only finitely many. Only finitely many disks. And because there are only finitely many disks, we can do this for all of them at once. So we can find one n. So if originally we have over here, this would be an n sub j. Then we take the maximum of all the n sub j. And that will make this less than epsilon. So this term now is less than epsilon. For this term, we have the fact that we're now within a very small distance of the point Wk. All right, so now let's go back to what we know. We know that our function is equicontinuous on compact sets. And so by the equicontinuity, now this will be small. And then the same argument is going on over here. So we first reduce to convergence at the Wk's. The Wk's are dense. They give us an open cover over a slightly expanded set, but it's okay. Everything we've done works on slightly expanded sets. Now that we have the results on slightly expanded sets, we then add 0 twice. And the whole point is we want to break the analysis to what's going on at points Wk, because it's the points Wk we understand. The middle one is actually the easiest one to understand. That's because we have forced ourselves to have convergence there. For the other ones, we are close to the Wk's, and we can just assert that z is sufficiently close to one of the Wk's. Why? Well, we're controlling what the radius is. The radius of these balls is delta. So by equicontinuity, we have these wonderful bounds that only depend on the compact set K. So we can make this sufficiently small. Now, the compact set is actually going to be a little bit inflated, but it will still be within omega. All right, so this finishes the proof of Montel 2. The main thing was to get through Montel today so that we do not have to split the argument. There's one other result we need. If you have a sequence of holomorphic injective functions, it converges to either an injective holomorphic function or a constant. Can somebody give me a sequence of holomorphic functions that converges to a constant? Holomorphic injective functions that converge to a constant.
Sequence of constant functions, or a sequence of functions that are all constant?
Yeah, but I want injective. Okay,
1 over nz.
1 over nz. Okay, how are you phrasing 1 over nz?
If your sequence is f of n's, and then n is a real constant term.
Right. Is it 1 divided by n times z?
Yes.
That'll work, but then we've got to just make sure we stay away from the origin.
All right. Yeah.
So if you just did something, a minor tweak of that, you'd be very safe. No,
No.
you're very close.
Z over n.
Z over n,
Yeah.
right?
No, that's what I meant. 1 over n times z.
Oh, well, okay. Oh, yes.
What is 1 over n?
Yeah.
Right. When you're saying 1 over nz,
Right.
right.
Yeah.
Z over n.
Right.
Yes. Okay. So I feel like this is an old comedy shtick. Who's on for no? So if we take something like z divided by n, as n gets very, very large, it's converging to the constant 0. If we could take z over n plus 5, and that will converge to the constant function 5. So you can't have a sequence of injective functions that are converging to a function that's constant. You want to make sure that doesn't happen. And so when we do the proof of the Riemann mapping theorem, we want to make sure we stay away from something like that. Well, we'll be looking at places where the first derivative is not 0, so that will basically force the functions not to be constant if the derivative is not 0. And then we'll get that these holomorphic functions will converge to an injective function. All right, So this is a good place to stop. I apologize for getting confused a little bit at the end in terms of all the different Cauchy criteria. And then we will prove the Riemann mapping theorem on Wednesday.